Traveling between the stars at speeds of 10 to 20% the speed of light is immensely challenging. There's a myriad of reasons why this is so, such as how do you propel your spacecraft to those speeds, and how do you protect your spacecraft against collisions with interstellar dust. But those are engineering challenges. Physics imposes a more fundamental problem, and that is the question of energetics. Take the now retired NASA Space Shuttle as an example. It's a relatively small object, 37 meters in length, a maximum crew capacity of 8 individuals, and with a mass of just over 100,000 kilograms, including cargo. Let's leave all the engineering questions aside and just ask the question, how much energy would it take to accelerate the space shuttle to, say, 20% the speed of light? Einstein's theory of special relativity allows us to compute this number precisely. The kinetic energy of any massive object is given by the following formula, where m is the object's mass, v is the object's velocity, and c is the speed of light in a vacuum. Plugging in the numbers, it's easy to show that the kinetic energy of the space shuttle traveling at point 2c would be 200 billion joules. It's difficult to conceptualize just how much energy we're talking about here. It's the total energy produced by 60 million Hiroshima atomic bombs. That's twice the total electrical energy produced by humanity in a year. And of course, there's also the issue of how one could possibly store up so much energy in preparation for the launch day. To make matters worse, it's not possible to convert our generated energy into pure kinetic energy. There are losses, and these inefficiencies mean that it actually costs far more energy than even this. Let's imagine that the shuttle was propelled by a giant laser system, such as that proposed for the breakthrough Starshot project discussed here in previous videos. The proposal is that a laser is fired from the Earth, reflects off the spacecraft, and thereby imparts a momentum kick to the shuttle, leading to locomotion. We can calculate the laser energy required, assuming perfect mirrors, perfect lasers, and it's given by equation 17 in my 2017 paper on the topic, which I'm showing here. This increases the energy required for our space shuttle by a factor of 5.5 times, which equates to an efficiency of 18%. That's because after each reflection, the photons in the laser beam have not been converted into pure kinetic energy. Rather, they have been reflected, donating only a small fraction of their energy to the shuttle itself. And so herein lies the fundamental and unavoidable challenge of so-called relativistic flight. Energy. There's no loopholes here, there's no workarounds to exploit. Massive objects moving at relativistic speeds have to somehow acquire vast amounts of kinetic energy. And so before addressing the myriad of engineering problems that will surely also come to bear when designing such a spacecraft, any serious discussion about relativistic flight has to first begin with the question of energetics. It was this conundrum which ultimately inspired my new work on the so-called halo drive. If we need astronomical levels of energy to accelerate spacecraft to relativistic speeds, then perhaps we could steal it from astronomical bodies. In particular, the halo drive harvests this energy from black holes.
I will travel where no man has dared to go.
Into the black hole?
In, through, and beyond.
The halo drive concept is covered in more detail in my last video, but let's just do a quick recap here to remind ourselves. A spacecraft near a binary black hole fires a laser beam towards one of the black holes at the instant when it appears to be approaching the ship. The beam is aimed such that it follows what's known as a boomerang geodesic, where it skims above the event horizon and gravitationally bends round 180 degrees to return to your ship. As it does so, it picks up momentum from the moving black hole in the same way that light Doppler shifts when reflecting off a moving mirror or emitted from a moving source, and thus it increases in energy, becoming bluer in color, a topic we've covered here on this channel in the past. The momentum exchange of firing and then receiving back the beam ends up propelling your ship away from the binary. That's Newton's third law. Every action has an opposite and equal reaction. Moreover, the beam returns with more energy than it left, allowing one to store this energy for further propulsion. But make no mistake, this is not energy from nothing. That's energy stolen from the black hole. My Halo Drive paper shows that a spacecraft of essentially arbitrarily large mass can accelerate up to approximately 4/3 the speed of the black hole using this method, remarkably without ever expending any fuel in the process. For compact binary black holes which orbit one another at relativistic speeds, this means that one could achieve relativistic flight without having to actually ever generate the aforementioned vast amounts of energy needed. Rather, you stole it. A cosmic heist, if you will. Many of you engaged with that video and asked lots of great questions in the comments section. So today I thought we would step through the Halo Drive again, but go into much more detail, more depth about how this process really works, and then get into some of the more extreme possibilities that might arise as a result of this technology. The Halo Drive can be thought of as simply a twist on the more familiar and conventional gravitational slingshot idea. In essence, the Halo Drive performs this gravitational slingshot remotely from a safe distance. But in both cases, the case of a conventional slingshot or the Halo Drive, kinetic energy is being transferred from the planet or the star to the spacecraft itself. One might wonder then, could we use the Halo Drive on objects other than black holes, such as a planet like Jupiter? Certainly, one can perform conventional slingshots around Jupiter, and indeed we have done so numerous times. But Jupiter is not moving fast enough to give a velocity kick to a spacecraft any greater than something like 20 kilometers per second, far below the speed of light. In going from a conventional gravitational slingshot to the Halo Drive system, the overall velocity change is approximately the same. However, unlike a binary black hole, Jupiter is not a particularly hazardous environment, and thus there is really no need to perform this slingshot from a remote distance. Moreover, the Halo Drive won't even work here because Jupiter's gravity is insufficient to deflect light into a so-called boomerang geodesic. Even the Sun only deflects light by 1/4 of 1,000th of a degree. That's a long way off 180 degrees. This is why a black hole is so critical. Only an object with an event horizon is capable of deflecting light so strongly. So yes, a black hole is always necessary, but does it always have to be a binary black hole? Well, actually here we do have some wiggle room. If we had a stationary, isolated black hole, then we could still indeed use the system to create the halo of light around it, thereby pushing the spacecraft away. However, the lack of any black hole motion here means that the light comes back redshifted each time, meaning the laser beam is hemorrhaging energy. So yes, you can still use the Halo Drive to accelerate away from a stationary black hole, but there's no free lunch here. In fact, rather than stealing energy from the black hole as we did before, we now actually end up depositing energy from the spacecraft's energy reserves into the black hole itself. But there is an effect which would change this picture, known as frame dragging. Via the famous no-hair theorem, black holes are completely described by just three parameters: their mass, rotation, and charge. Generally, we don't expect black holes to retain any significant charge, but rotation is a different matter altogether and something we have not discussed thus far. Remember that black holes are the remnants of dead stars, stars which once upon a time would have presumably had some arbitrary rotational energy to them. As they implode, massive stars dramatically shrink down in size by factors of many thousands. They thus spin faster via the conservation of angular momentum, much like how an ice skater spins faster as they tuck in their legs. And so in general, black holes are expected to be rapidly rotating, plausibly at extreme speeds. Objects sometimes called Kerr black holes, after Roy Kerr, who first derived their space-time metric in 1963. As black holes spin, their intense gravitational field drags space-time around with it, an effect known as frame dragging. This frame dragging effect, as caused by the Earth, has even been observed using the Gravity Probe B experiment. Now imagine our halo drive being operated in the vicinity of such a black hole. First, the necessary boomerang geodesics have been proven to exist for these Kerr black holes by Claes Kramer in 1997. Second, if we imagine firing our laser beam such that light moves in a prograde manner with the frame dragging effect, it should be expected to pick up momentum during its close passage, just like we did for the binary black hole case. In the case of binary black holes, you might remember in the last video that I gave you this analogy of thinking about bouncing a ball off a moving wall as a way of understanding why it is that photons can pick up momentum from the black hole. Now here things are clearly a bit different. I think a better analogy here might be to imagine stepping onto a merry-go-round for just half a rotation and then jumping off again. When you jump off, you will be moving faster and thus have stolen some kinetic energy from the merry-go-round. In the same way, light riding along the frame-dragged space-time, a cosmic merry-go-round if you will, should be expected to pick up momentum and, like before, become blue-shifted. This satisfies our requirement for the halo drive system, and thus, indeed, binary black holes are not the only way to accomplish this feat. A spinning black hole will also work, a topic touched on in my original paper. Because of the immense spin-up that occurs as they collapse, black holes can potentially spin up to speeds approaching the speed of light. And indeed, we have observed more than a dozen cases of black holes doing exactly this. I actually think that the case of the spinning black hole might be the more viable location to undergo this halo drive system. However, in the paper, I mostly focus on the binary black hole case, largely because the mathematics is considerably simpler than dealing with this frame dragging effect. Nevertheless, we have two possible locations now where we could use this halo drive system. So let's discuss what this journey from the black hole would really be like. Let's talk about this journey away from the black hole. In general, the starting position for your spaceship really needs to be within the same system as this black hole, but not too close to avoid being ripped apart by the intense tidal forces of the singularity. Orbiting at a distance of a few hundred times the black hole's Schwarzschild radius, that's the distance from which even light cannot escape the black hole, should be sufficient for typical parameters in order for this spacecraft to resist the tidal stresses. The halo drive works best when we choose a destination which lies in the same orbital plane as the rotational axis of the black holes. Now, if you want to make a journey out of the plane, that is still possible, but you will not be able to achieve quite as fast a velocity. To head to your destination, all you really need to do is simply wait. You orbit the black holes until you line up with your destination, you fire up your halo, and you will be pushed out of the system. Now, obviously, this will take very precise timing and accuracy with the beam, but you might expect an onboard computer to handle those calculations in real time for you. As the beam leaves the ship and loops back around, it will start to diverge in width due to diffraction. Too much divergence and the beam will largely miss the ship on the way back. At the initial starting distance, any laser beam with a wavelength less than mid-infrared light, such as visible light for example, is shown in my paper to result in negligible diffraction. Gravitational tides also act to try and diverge the beam, but critically here the non-stochastic nature of those tides make them correctable using precise laser actuators on board your spacecraft. Once you've fired this beam, it will actually take less than a fraction of a second to make its loop around the black hole. That's because we don't have to worry about time dilation really here. Light always has to travel at the same speed to all observers. That's the speed of light, c. Because the black hole represents a gravity well, light blue shifts somewhat as it rolls down the hill and then red shifts as it comes back out, an effect known as gravitational redshift. It turns out that these effects effectively cancel out as shown in my paper, and thus the effect can largely be ignored when it comes to the energy balance calculations. The ship then starts to accelerate, and the rate of acceleration is essentially completely up to the crew, because the way in which this ship is accelerating is via an impulse imparted by the emission and reception of this beam. If the crew was simply an artificial intelligence of some kind, then the acceleration limit would largely be a function of the ship's material strength. If instead we imagine human astronauts on board, then one might want to limit the acceleration to 1g. 1g acceleration, however, would pose a fairly serious problem for the halo drive, because at 1g acceleration it would take you 70 days to reach 20% the speed of light, by which point you would be so far away from the black holes that beam divergence would become a major problem. It may be possible to position numerous dynamic lenses along the initial part of the route, which would refocus the beam as needed. Although to be upfront, this is not something which was calculated in the original paper. Now once we're up to speed, we're not out of the woods yet because we still now have to contend with cosmic rays and impacts with the front of the ship from interstellar dust and interstellar gas, both of which themselves will induce a second form of hazardous radiation onto the ship. For velocities below 30% the speed of light, the generated nucleonic radiation could be shielded against with just 1 to 2 centimeters of titanium hull. That's according to calculations by Oleg Semyonov in 2006. Cosmic rays, on the other hand, would require more mass. A water shell of, say, several meters would provide similar protection to that experienced here on the Earth. Bombardment with interstellar gas at 20% the speed of light would penetrate the hull to approximately 0.1 millimeters for a dense forward shield. That's according to recent calculations by Thiem Huang et al. Dust bombardment is more problematic though, leading to explosive evaporation and cratering on the hull's surface and eroding the surface down to about 0.5 millimeter. So these are clearly major challenges, but they are also clearly easily surmountable with adequate shielding. And after all, the halo drive is able to accelerate arbitrarily large masses, and thus one really doesn't have a good excuse for leaving the system without that shielding on board. When we arrive at our destination, whatever kinetic energy that we gained as a result of using the halo drive in the first place, now we have to dispose of that kinetic energy in order to decelerate, in order to come to a stop at our destination. Deceleration is often a major challenge to a relativistic flight, so much so that Breakthrough Starship really doesn't even attempt to solve it and simply plans to perform a relativistic flyby of its target. Can we do any better here with a ship powered by this halo drive? Fortunately, yes, but again, we're going to need a black hole to make this work. As we approach a destination black hole, we fire the laser once again, performing yet another boomerang geodesic. So when the light leaves the front of your ship, it will give you a slight momentum kick in the opposite direction, thereby slightly slowing you down. And also when the light loops around and hits your spacecraft, it will give you another kick again in the opposite direction, further decelerating you. Also, like before, the photons come back with more energy than that which they left with. In other words, they are blue shifted as a result of this relative motion between you and the black hole. That means you can again charge up your batteries, and that stored energy will be useful for maneuvering into a stable orbit at the end of the deceleration. The beauty here is that you don't even need a binary or even a spinning black hole to break. Any will do. Of course, the former two cases would be more useful if you ever plan to leave the system again. I have to admit that the idea of hurtling towards a black hole at 20% of the speed of light is a fairly disconcerting thought. After all, your life now hangs in the balance as to whether this halo drive system will work. Any slight miscalculation or malfunction, and you will fling yourself straight into the black hole and be torn apart into pieces as a result of the tidal forces. This journey is not for the faint of heart.
If you can't take a little bloody nose, maybe you ought to go back home and crawl under your bed. It's not safe out here. It's wondrous, with treasures to satiate desires both subtle and gross. But it's not for the timid.
From the perspective of the halo drive, black holes represent waypoint stations, special places where we can accelerate and decelerate huge starships to potentially relativistic speeds. In this way, they form an intra-galactic network, a highway system for interstellar travel. But how many black holes are really out there? From our understanding of stellar evolution and recent observational constraints from the LIGO detector, about 1 in every 1,000 stars becomes a black hole, meaning that roughly 100 million black holes reside in our Milky Way galaxy. Unfortunately, the location, distribution, and basic properties of these black holes is largely unknown to us. And that's because these black holes are, of course, by their very nature, incredibly difficult to detect. Statistically speaking, the nearest black hole should be about 12 parsecs away. But we actually don't know where that black hole is yet. Nevertheless, 12 parsecs is a distance we can plausibly imagine sending a spacecraft to one day, through concepts such as Daedalus and Starshot. All-sky photometric surveys such as WFIRST and LSST may be able to detect some fraction of the galactic black holes as they pass in front of distant stars and lens the background light. Future gravitational wave detectors such as LISA are expected to spot so many compact binaries in our galaxy that they will be a significant source of noise for the detector, with an estimated 25,000 detections amassing in the first few years. Clearly, before we can ride on this interstellar halo network, we first have to have a good map of the location of all of these nearby black holes. But that is one area of astronomy where we are indeed making the most rapid progress. So we should be excited about the future here. Even so, making trips across interstellar distances, particularly across the galaxy, would still be a very trepidous enterprise. For instance, one might need to account for galactic tides and peculiar stellar motion of these objects. Similarly, the population of compact binary black holes is in essence in a state of flux, with mergers occurring and wider binaries constantly evolving into more compact states. A common question I got asked on the last video was, if you have to travel to the nearest black hole in order to utilize this halo drive system, then doesn't that somehow make the halo drive system of no value? Let's consider an analogy of 19th century USA representing the galaxy. Imagine you lived in Orlando in the year 1870, one of just a few dozen inhabitants at the time. Nothing compared to the hundreds of thousands of people living in the cities of Philadelphia, Boston, or New York. Despite living in this tiny hamlet on the outskirts of the USA, you dream of one day visiting California, a distant land you've only read stories about. Yet, the vast distance to cover defies ordinary understanding, a distance so great that even on horseback it would take you months of riding. Moreover, it would cost you so much in food reserves and equipment that even if you made it there, you'd be broke without any chance of being able to ride back home again or explore indeed any other part of this great land. It seems hopeless, perhaps best just to stay at home. But then someone tells you about railroads being built in nearby Jacksonville, just a few days' ride away on horseback. If you can get to Jacksonville, you can ride along the East Coast and even connect to the new Pacific Railroad, taking you to California in just a week. And the cost? It's free. Yes, it will cost you to hire a horse and ride up to Jacksonville, but if you get there, you can ride across the entire country for free, as many times as you like. So yes, riding the Halo network comes at a cost. That is, you have to journey to the nearest black hole. And similarly, riding the rail network comes at a cost too. You have to travel to the nearest rail station. But unlike 19th century USA, there's no cost after that point. So personally, I don't agree that there's no value to a galactic highway system. It's going to take a bit of work, but pay the cost to reach the nearest station and the galaxy opens up. Hopefully that should provide us with an extra incentive to reach the nearest stars and leave our home. Let us finally address what other uses an advanced civilization might have for a Halo system like this. Now, critically here, there's no real free lunch. The energy which we're using to power our propulsion system is being stolen from the gravitational binding energy of the binary black hole, or in the case of the Kerr black hole, it's coming from the rotational energy of that object. Over time, this will erode away that rotational energy and thus will eventually cause, for instance, binary black holes to merge. The total amount of energy stored in a binary depends on its specific properties, but it can be of order of a solar rest mass or even higher, converted into pure energy. That's a monstrous amount of energy, equal to the power output of all of the luminous stars in the Milky Way combined, shining for 1,000 years, which means that a Kardashev Type 3 civilization could feed off it for a millennium. As an example of this, when LIGO observed GW 150914 merge in 2015, that's the pair of binary black holes it saw, the peak power output actually exceeded that of all of the stars in the observable universe. There is a lot of power to be had here. I've spent a bit of time thinking about how a civilization could siphon all of this energy from the black hole, but avoid the propulsive aspect of the Halo drive system. And frankly, it's going to be very difficult to make that work. Conservation of momentum wants to push this spacecraft or this orbiting station out of the system. And so I can't really think of a good way to get around that. But if you have ideas on how that might work, then I would love to hear about them. Nevertheless, we might expect a civilization to reside around these waypoint stations in much the same way that human settlements and cities tended to spring up around trade hubs. These cosmic oases may represent common meeting points between different peoples, a watering hole between the vast emptiness of interstellar space. We may even be able to detect the presence of such civilizations remotely by virtue of the fact that black holes would appear to merge at a slightly elevated rate compared to that expected naturally, or even that the binaries could be kicked into eccentric orbits pointing along the preferential lanes of interstellar travel. Once we know the location of nearby black holes, they could become a target for radio searches and other technosignatures too, which are, to say, indications of industrial activity occurring around these Halo waypoints. There's a lot of exciting potential that one could imagine advanced civilizations using for this Halo drive concept here, but just because we can imagine it doesn't mean that necessarily anybody is using it. We can certainly think of reasons why they might do this, much like the famous Dyson sphere concept, but ultimately it's impossible to know whether other civilizations actually choose to do so, or indeed what our distant future ancestors will do. For me, frankly, thinking about these concepts is an awful lot of intellectual fun, to think about what paths we might one day follow. It's pretty hard to make a career out of doing this kind of research, but I encourage all of us to spend some small fraction of our time thinking about really big ideas like this. Before any revolution, there has to be a dream. So until the next video, stay thoughtful and stay curious.